Hello everyone, welcome to the second video of the Intro to Quantum Computing video series. In the previous video, we went over classical information processing, the type of information processing that is used in our computers today. In particular, our computers today are built on fundamental building blocks called bits, which operate based on the rules of classical physics. That is, the branch of physics that sprung from Isaac Newton in the 1600s. These computers are therefore called classical computers, which make up the computer, phone, or tablet that you are watching this video on, and practically any other device that you've used until today. If any of this is unfamiliar, make sure to check out the link in the description to the previous video. In this video, we are making a fairly big leap, though one that can have profound impacts on the capabilities of computers. We will talk about quantum information processing, which scientists are working on today as the basis for a new type of computing. Scientists are working to build a different type of computer, a quantum computer, that runs on the rules of quantum physics. This is the physics that sprung from the work of Albert Einstein, Niels Bohr, Max Planck, and others in the early 1900s. Our goal is to understand what quantum information processing is and how it works. Before we do that, however, why are scientists working so hard to go from classical information processing to quantum information processing? If we are going to be spending some time talking about quantum information processing, it's important to understand why it is thought to be so worthy of pursuing in the first place. To gauge why quantum information processing is so powerful, first, let's imagine a circle. And this circle contains the set of all problems that we know classical computers can compute in a reasonable amount of time. Now, there are more complex problems outside of it that a larger circle encompasses. This is where quantum information processing, or QIP, lies. Because quantum information processing is based on the rules of quantum physics, there are certain more difficult problems that quantum information processing can solve in a reasonable amount of time. Some computations could be done much more quickly on a quantum computer. So if you thought that computers today are powerful, wait until we have a quantum computer. Quantum computers might allow us to perform computations that we couldn't even fathom, since we are currently bound by the limitations of classical computers and classical physics today. One of the computations that we know quantum information processing would be capable of is a famous algorithm theorized by Peter Shor, which uses the power of a quantum computer to factor large numbers in polynomial time. To give a sense of what this means, all of our bank encryptions today currently rely on the fact that it would take a classical computer an impractical amount of time to decrypt them, perhaps many years or decades. With a large-scale quantum computer, you could possibly do that in days, hours, or maybe less. Although this is a security threat, quantum information processing would allow us to do other types of more secure encryptions. Another example is database search, which uses an algorithm developed by Love Grover to find a specific element of information quickly from a large database. It's like finding a needle in the haystack. It may take a long time to find a desired element of information with a classical computer, but with a quantum computer, there is a real speed up. One of my favorite examples is the capability of using quantum computers to efficiently simulate quantum systems. Think about it. Chemistry, physics are all fundamentally running on the laws of quantum physics. So if we had a computer that operated based on these rules, it would theoretically be much easier to simulate such systems in this computer. This was first proposed in the 1980s by David Deutsch and Richard Feynman. As exciting as these examples are, this is just the tip of the iceberg. There are thought to be many more hard problems that could lie in this outer circle. We don't know how many other hard problems are solvable with quantum computing, or what they are, and that's an active area of research. The key takeaway is that quantum information processing is a much more general type of computing than classical information processing. It contains classical information processing, but also goes significantly beyond it. Now, the question is, how do we get there? Well, this may seem out of this world, but really, we can base how a quantum computer works on how a classical computer works. Fundamentally, a classical computer stores and processes information using its fundamental building block, the bit, which can be in the 0 or 1 state. You can also think of the 0 state as facing upwards and the 1 state as facing down. Now, in quantum computing, we have something similar. We have a quantum bit, or as I like to call this cute little guy, Mr. Qubit. However, here you see Mr. Qubit in one of his possible states. He is pointing up. But this is not Mr. Qubit. Mr. Qubit can be pointing either up or down, or he can be pointing in both directions at the same time. Yes, you heard it right, at the same time. Now, the qubit is the fundamental unit of information in a quantum computer. And similar to how we represent a classical bit with 0 and 1, we can represent quantum mechanical states in what's called Bloch notation. Up is represented as a 0 ket, and down as a 1 ket. Now, we can represent a qubit as being in one of these two possible states, or in a combination of them, mathematically called a linear combination. The linear combination of states is a unique quantum property, as we'll see in a little bit. From an information storage perspective, this brings us to a whole new level compared to the classical bits from the previous video. The classical bits, in stark contrast, could only ever be in either the up or the down state at once. They could only ever be in 0 or 1, meaning that the information that they store is limited to these two states. However, one quantum bit like Mr. Qubit breaks this limit and stores even more information. Imagine that you wanted to store the same information as a qubit, but classically. You would require a lot more than a single bit of information to specify an arbitrary state of a qubit exactly, and we'll see more about this later. So, the fundamental building block of a quantum computer can store more information than the fundamental building block of a classical computer, and is all in all a very different type of object. Now, the fact that Mr. Qubit can be both up and down at the same time might be confusing, and if you are confused, you have good reason to be. This doesn't really align with how we know the world to be and might seem counterintuitive at first. However, this phenomenon is exactly what we observe at the level of fundamental particles in nature, so it's something that we know is possible and exists. Let's take a look at one experiment that shows this mysterious nature, the one that revealed to us the possibility of quantum behavior occurring in real life. This is called the double slit experiment, which you may have heard of in a physics course, but here we see how it's tied to quantum computing. In this experiment, we start with a single source of particles. These could be electrons or photons, for example, and a screen that they are expected to land on. The particles must travel, however, through an obstacle course. They must go through two slits before landing on the screen. When they do land on the screen, a little mark appears. This is called a measurement outcome, a measurement of the particle's position on the screen. Now, the particles can be any type that exhibit quantum properties, like electrons or photons, meaning that they are small enough to be ruled by the laws of quantum mechanics. Here, we show a source of electrons, these little buddies here in green. A bunch of electrons are beamed towards the double slits. Zooming in onto what happens with one electron, we see it arriving at the slits. What should I do? It thinks to itself. Should I go through the left or through the right? We expect the electron to choose, and after many electrons have been sent through and chosen either slit, we expect there to be two lines on the screen, indicating where the electrons have landed. However, in reality, this is not what scientists observed when conducting the experiment. Instead, they observed this pattern. Peculiar, very peculiar. Why does this mysterious phenomenon happen, you may ask? Well, after scientists pondered at the possible reasons for this new existential crisis of physics, they realized that there was only one possible explanation. The electron did not really decide to go through either slit. It did not make a choice. Instead, it was indecisive and behaved like a wave that can be in all places at once. It went through both slits at the same time. While waves are known to characterize rays of light, it was surprising and baffling to see this continuous flow happening in a particle that was thought to be a discrete entity. This groundbreaking discovery for the behavior of a particle was given a name, wave-particle duality, in which a particle acts like a wave. Now, how exactly did this explain the observed pattern on the screen? How does the particle acting like a wave produce the pattern? Well, we have our beam of particles that arrive, and when they cross through the slit, it is like we have two new sources of waves, one from the left slit and one from the right. And importantly, these waves can interfere with each other. They can overlap. The pattern that results is because in some places you have constructive interference, where the waves add to a larger amplitude, and others destructive interference, where the waves cancel each other out. Just like we see in waves of water or light, but with particles. Now, where have we heard of an entity that can be in multiple places at once? Aha! Mr. Qubit. Both the electrons in the double slit experiment and qubits exhibit a property called
superposition.
What? Who said that? Anyways, superposition is when a particle can be in multiple states, or a combination of those states at the same time. Here, the electron has infinite positions that it can be in over all of space. It has a superpower. It has a superposition. Get it? Whoever said that physicists weren't creative. So, the position of the electron before it hits the screen is in superposition over all space, meaning it can land in any position on the screen. There's an infinite continuum of all the possible positions that the particle can land in. In technical terms, there's an infinite number of measurement outcomes on the screen. In comparison, the qubit has only two possible measurement outcomes that it can be in a superposition of, the up state and the down state. Before measuring the qubit, it can be in a combination or superposition of the two states. But after we measure it, like a particle landing on a screen, it collapses to one of its two possible states. So we can see a clear relationship. Whereas the electron represents a quantum system with an infinite number of measurement outcomes, a qubit represents a quantum system with a finite number of measurement outcomes. In fact, a qubit is the smallest type of such quantum system, since it can be in a superposition of only two possible states and has only two possible measurement outcomes. We can use something called a wave function to predict where the particle will land. This here is the wave function notation, and it is the amplitude of the wave representing the particles in the double slit experiment. The wave function squared tells us the probability of the particle landing at a certain position x on the screen. For example, if the probability was 0 at a point x on the screen, this means that there is 0% chance that the particle will land there. If the probability was 1, then the particle would land 100% of the time in the same spot, meaning we would know exactly where it would land, though this never happens in real life. If the particle was 1/2 at one spot, then we would know that the particle lands there 50% of the time. We can also have any probability we wish in between. But how do we know this probability? Well, the wave function is a quantity that theoretically predicts the probability of an electron landing somewhere. The wave function is based on the geometry of the slits, the momentum carried by the particles, and the distance between the slits and the screen. We can verify the wave function's predictions by making many measurements, many experiments, and seeing how often particles will land in different spots on the screen. Note that when conducting an experiment, if we have one particle, we don't know where it will land. As far as we can tell, that is completely random. However, if we perform many experiments in aggregate, we can start to tell the probabilities of particles landing in the different spots. We can start to see the pattern, and the wave function predicts these patterns, not where a single particle will land. And so let's go back to our qubit. The qubit, recall, is the fundamental building block of a quantum computer. It can be in a combination of states, 0 and 1, known as
superposition
of these states. And we can tell the probability of the qubit being in each of these states from the wave function. To denote this, we use the Greek letters alpha and beta. Alpha and beta are the amplitudes of the wave function, the amplitudes of each qubit state. To denote the superposition of a qubit, or the wave function of a qubit, we sum the two states and show their amplitudes. We have 0 plus 1 with coefficients alpha and beta. And similar to how we had the probabilities of an electron landing in a spot before, now we can denote alpha squared as the probability of being in the 0 state, and we can denote beta squared as the probability of the qubit being in the 1 state. And this is how we represent Mr. Qubit mathematically. Now note that alpha and beta are called complex coefficients, meaning that they are not restricted to real numbers, but can be complex numbers, combinations of real and imaginary numbers. Now imagine we have a sphere. This sphere represents our qubit. This is called the Bloch sphere, and it allows us to visualize the state of the qubit. Here, we can see Mr. Qubit pointing up. Before, we had classical positions of up and down, which the qubit can also be in. When it's up, it is in the 0 state, and down, it is in the 1 state. The qubit, however, can also be in a superposition, a combination of the two states, anywhere in between the up and the down states. When it's in the equal superposition, it is pointing exactly along the equator, and we can represent this mathematically as 0 plus 1 over root 2, and we'll see why in a second. To get to this equal superposition state from the 0 state, we have to go through all of the other states in between, starting at the upward state and rotating through the different superpositions along the sphere. We can see that as we rotate, the amplitude of the up state is decreasing and the amplitude of the down state is increasing until we get to the equal superposition of the two. From the equal superposition, we can get to the down state by once again rotating along the sphere through the additional possible superposition states. Now, the down state is increasing in amplitude even more until the up state disappears. Here, we just show a few of the possible states, but there are actually an infinite number of choices in between. And if you think about it, specifying an arbitrary qubit state is like specifying a position on the Earth. To do it with perfect accuracy, we would require specifying two angles, each with infinite precision. And like we can travel anywhere on the Earth, we can travel anywhere on the sphere. Before, classical bits only had the up and the down states, which are at the north pole and south pole of the Bloch sphere. Now, qubits can be anywhere in between these states as well. They can be in superposition. The qubit, therefore, in a manner of speaking, is more flexible and can store much more information than a classical bit. We can represent the probabilities of being in each state. In the first state, we begin with a 100% chance of being up and no chance of being down. We are in no superposition here. When we start to rotate, one of the next states could be 90% up and 10% down. Next, we could rotate more and go to a state that is up 75% of the time and down 25% of the time. Then 65% up, 35% down, and finally 50-50. Once again, note that these are superpositions of states. Now, here's something cool. To get from the up state, or the 0, to the equal superposition, we actually do a pi over 2 or 90-degree rotation of the sphere. And now, we can see why the equal superposition state is written like this. If we split the state up into its building blocks, we have the following. And each state has an amplitude of 1 over root 2. They have an equal amplitude where alpha is equal to beta. This means that the alpha squared is equal to beta squared, which we can rewrite as 1 over root 2 squared is equal to 0.5. So alpha squared equals 0.5 and beta squared equals 0.5, which is where the 1 over root 2 in the equation comes from. So you can see how the notation tells us what the probability of each state in the superposition is, and how we can represent that on the Bloch sphere. To sum up what we've seen is that we've created a way to store and process information in a qubit. To go from the up or the 0 state to the equal superposition state, we started with an input state, and then we rotated the state along the sphere, or performed an operation on it to get to the output state. This operation is called a gate, and gates, for a single qubit, can be any rotation of the Bloch sphere around any axis, like traveling along the Earth's surface. Think of all the unique places you could visit. This is analogous to the many possible states of a qubit. In contrast, a classical bit, as we saw in the last video, can have an input state of 0 or 1 and can only be flipped or rotated 180 degrees to get to the output state of 1 or 0. So, all in all, operating on a qubit with gates is how we process information. Now we can see one of the main reasons for why a qubit is so special in information processing. In classical computing, we can only change bits from one state to the other by rotating 180 degrees. But in quantum computing, we can change a qubit from one state to the next by performing any rotation from 0 to 360 degrees about any axis. And in quantum computing, this is possible because of the fundamentally quantum nature of qubits, of being in superposition. Woohoo! That was a lot. Give yourself a pat on the back for making it this far. Let's sum up. In this video, we learned that the analog of a classical bit in quantum computing is the qubit, or the quantum bit. Mr. Qubit's quantum nature can allow it to be in a superposition of states, just like an electron can be in a superposition of states in the double-slit experiment. This is one of the fundamentally different properties of quantum bits that can help us achieve our goal of more powerful computations. We can visualize all of these qubit superpositions on the Bloch sphere, and we can use the Wavefunction to calculate the probability of Mr. Qubit being in one of its basis states. Lastly, we can process information in a qubit or change its state using quantum gates, which are simply rotations of the Bloch sphere. Now, feel free to take a breather, rewatch anything you like, because things are going to get more interesting in the next video. Up until now, we've been talking about one qubit, which is simple when you think about it as just a sphere that can be rotated to represent different states of information, right? However, just like we can't do much with one classical bit, we can't do much with one qubit either. We need a system of qubits to be able to represent and process more information, to perform useful computations. Only then can we hope to realize the capabilities of quantum computers, such as factoring of large numbers, quantum simulations of chemical and biological systems, database search, and more. Join me in the next video to see how we can expand our horizons into a multi-qubit system and move closer to realizing the powers of quantum computing. This video was written, narrated, designed, and musically composed by Romi Lifshitz. Thank you so much to Professor Jonathan Bloch from the University of Waterloo's Institute for Quantum Computing for his immense support in making this video. The Ball Lab is working on exciting physical devices that will enable quantum information processing. To learn more about their amazing work, be sure to check out the link in the description and tune in to the next video.